What I'm going to attempt to do in the next few videos is really just give an overview of everything that's happened to Earth since it came into existence. And we're going to start really at the formation of Earth, or the formation of our solar system, or the formation of the sun. And our best sense of what actually happened is that there was a supernova in our vicinity of the galaxy. And this right here is a picture of a supernova remnant, actually the remnant for Kepler's supernova. The supernova in this picture actually happened 400 years ago in 1604. So right at the center, a star essentially exploded, and for a few weeks was the brightest object in the night sky, and it was observed by Kepler and other people in 1604. And this is what it looks like now. So this is what we see as kind of the shock wave that's been traveling out for the past 400 years. And so now it must be many light years across. It wasn't, obviously, matter wasn't traveling at the speed of light, but it must have been traveling pretty fast, at least relativistic speeds, where a reasonable fraction of the speed of light. So this has traveled a good bit out now. But what you could imagine is when you have the shock wave traveling out from a supernova, let's say you had a cloud of molecules, a cloud of gas, that before the shock wave came by, it just wasn't dense enough. It wasn't dense enough for gravity to take over and for it to accrete essentially into a solar system. But when the shock wave passes by, it compresses. It compresses all of this gas and all of this material and all of these molecules. So it now does have that critical density to form, to accrete into a star and a solar system. And so we think that's what's happened. And the reason why we feel pretty strongly that it must have been caused by a supernova is that the only way that the really heavy elements can form, or the only way that we know that they can form, is in kind of the heat of a supernova. And our uranium, the uranium that seems to be in our solar system on Earth, seems to have formed roughly at the time of the formation of Earth, at about 4.5 billion years ago. And we'll talk in a little bit more depth in future videos on exactly how people figure that out. But since the uranium seems about the same age as our solar system, it must have been formed at around the same time, and so it must have been formed by a supernova, and it must be coming from a supernova. So a supernova shock wave must have passed through our part of the universe, and that's a good reason for gas to get compressed and begin to accrete. So you fast forward a few million years ago, that gas would have accreted into something like this. It would have reached the critical temperature, critical density, and pressure at the center for ignition to occur, for fusion to start to happen, for hydrogen to start fusing into helium. And this right here is our early sun. Around the sun, you have all of the gases and particles and molecules that had enough angular velocity to not fall into the sun, to go into orbit around the sun. They were actually supported by a little bit of pressure, too, because you can kind of view this as kind of a big cloud of gas. So they're always bumping into each other. But for the most part, it was their angular velocity. And over the next tens of millions of years, they'll slowly bump into each other and clump into each other. Even small particles have gravity. And they're going to slowly become rocks and asteroids, and eventually what we would call planetesimals, which are really, you could kind of view them as seeds of planets, or early planets. And then those would have a reasonable amount of gravity, and other things would be attracted to them and slowly clump up to them. But this wasn't like a simple process. You could imagine you might have one planetesimal form, and maybe there's another planetesimal form. And instead of having a nice, gentle, those two guys accreting into each other, they might have huge relative velocities and ram into each other and then just, shatter. So this wasn't just a nice, gentle process of constant accretion. It would actually have been a very violent process. It actually happened early in Earth's history, and we actually think this is why the moon formed. So at some point, you fast forward a little bit from this, Earth would have formed, or I should say the mass that eventually becomes our modern Earth would have been forming. Let me draw it over here. So let's say that is our modern Earth. And what we think happened is that another protoplanet, or it was actually a planet because it was roughly the size of Mars, ran into what is eventually going to become our Earth. And this is actually a picture of it. This is an artist's depiction of that collision, where this planet right here is the size of Mars, and it ran into what eventually would become Earth. And this we call Theia. This is Theia. And what we believe happened, and if you look up if you go onto the internet, you'll see some simulations that talk about this, is that we think it was a glancing blow, that it wasn't a direct hit that would have just kind of shattered each of them and turned them into one big molten ball. We think it was a glancing blow, something like this. So if this was essentially Earth. Obviously, Earth got changed dramatically once Theia ran into it. But Theia is right over here, and we think it was a glancing blow where it came and it hit Earth. It hit Earth at kind of an angle, and then it obviously the energies from that interaction would have made both of them molten. And frankly, they probably already were molten because you had a bunch of smaller collisions and accretion events and little things hitting the surface of probably both of them during this entire period. But this would have had a glancing blow on Earth and essentially splashed a bunch of molten material out into orbit. So it would have just come in, had a glancing blow on Earth, and then splashed a bunch of molten material. Some of it would have been captured by Earth. So this is the before, and then the after. The after, you could imagine, Earth is kind of this molten, super hot ball, and some of it just gets splashed into orbit from the collision. And let me see if I can draw Theia here. So Theia has collided, and it is, it's also molten now because huge energies, and it splashes some of it into orbit. And if we fast forward a little bit, this stuff that got splashed into orbit, it's going in that direction. That becomes our moon. And then the rest of this material eventually kind of condenses back into a spherical shape and is what we now call our Earth. So that's how we actually think right now that the moon actually formed. And even after this happened, the Earth still had a lot more, I guess, violence to experience. So just to get a sense of where we are in the history of Earth, we're going to refer to this time clock a lot over the next few videos. This time clock starts right here at the formation of our solar system 4.6 billion years ago, probably coinciding with some type of supernova. And as we go clockwise on this diagram, we're moving forward in time. And we're going to go all the way forward to the present period. And just so you understand some of the terminology, GA means billions of years ago, G for giga. MA means millions of years ago, M for mega. So where we are right now, the moon has formed, and we're in what we call the Hadean period, or actually I shouldn't say period, it's the Hadean eon of Earth. Period is actually another time period. So let me make this very clear. It's the Hadean, we are in the Hadean eon. And an eon is kind of the largest period of time that we talk about, especially relative to Earth. And it's roughly 500 million to a billion years is an eon. And what makes the Hadean eon distinctive, well, from a geological point of view, what makes it distinctive is it's really we don't have any rocks from the Hadean period. We don't have any kind of macroscopic scale rocks from the Hadean period. And that's because at that time, we believe, the Earth was just this molten ball of kind of magma and lava, and it was molten because it was the product of all of these accretion events and all of these collisions and all of this kinetic energy turning into heat. So if you were to look at the surface of the Earth, if you were to be on the surface of the Earth during the Hadean eon, which you probably wouldn't want to be because you might get hit by a falling meteorite or probably burned by some magma or whatever, it would look like this, and you wouldn't be able to breathe anyway. This is what the surface of the Earth would look like. It would look like a big magma pool. And that's why we don't have any rocks from there, because the rocks were just constantly being recycled, being dissolved and churned inside of this giant molten ball. And frankly, the Earth still is a giant molten ball. It's just we live on the super thin, cooled crust of that molten ball. If you go right below that crust, and we'll talk a little bit more about that in future videos, you will get magma. And if you go dig deeper, you'll have liquid irons. I mean, it still is a molten ball. And this whole period is just a violent, not only was Earth itself volcanic, molten ball, it began to harden as you get to the late Hadean eon, but we also had stuff falling from the sky and constantly colliding with Earth and really just continuing to add to the heat of this molten ball. Anyway, I'll leave you there. And as you can imagine, at this point, there was no, as far as we can tell, there was no life on Earth. Some people believe that maybe some life could have formed in the late Hadean eon, but for the most part, this was completely inhospitable for any life forming. So I'll leave you there, and we're going to, where we take up the next video, we'll talk a little bit about the Archean eon.